So we're gonna find so we're looking to find the deflection within the beam on the YZ plane. So in order to do that, so we're looking for delta. Okay, so in order to find our displacement, we're gonna first thing we need to do is find the principal axes of our cross section. So if our original axes are the Y and the Z axes, what we're looking for is we're looking for the axes, the principal axes M and N. Okay, so those are separated from our Y and Z axes by an angle of theta P. Okay, so we can, once we've determined our principal, and we talked about earlier how we can solve for that principal angle theta P using the tangent function. So once we have theta P, we can then resolve our bending loads uh, along our principal axes. So in order to do that, we can take, we can say that M of M and the moment about the n-axis would be equal to cosine theta P, sine of theta P, times m of y and m of z. And then our second row, our equation for mn, would be equal to negative sine of theta P times my plus cosine of theta P times mz. Okay. So using those two equations, we can find mm and mn, and then we can determine our deflection along the principal axes using beam theory. So we can solve for delta m, and we can solve for delta n. Typically, delta, if you look at like a textbook, will give you delta as a function of for a specific geometry and loading condition. It'll give you delta as being a function of the moment, the modulus of elasticity, the I, and then like the location or the length of the beam, x. Okay, so typically it'll be something that would be along this. That'll give you an equation for delta. So you can plug that in, and then you just have to use the corresponding moments of inertias, elastic moduli, and I for the correct axes to determine your equation. Okay, so then once you have sigma delta m and delta n, you can use the transformation equation again to solve for the deflection of the y and the z axes. So you can just write it as being equal to this equation here. Alright, where we have our transformation matrix, we're going to take the inverse of that transformation matrix because we're going from yz, we're going from mn to yz. So we have to take the inverse of that matrix and go here. Alright, so that will give us our delta y and delta z. You don't have to do that unless you're asked specifically for the deflection along the x or the y, or the y and the z axes. And then the last thing is we need to take the vector sum of our deflection. So we can say that our maximum deflection would be equal to, the maximum deflection squared would be equal to sigma x squared plus sigma y squared, which would also be equal to sigma m squared plus sigma n squared. Okay, so in conclusion, or in summary, what we did here is we first found our principal axes, m and n, using the equation for theta p. Once we have theta p, we can plug it in to solve for our bending moments about the m and the n axes using this transformation equation, transformation matrix. Once we do that, we can then determine the deflection about each of the principal axes using the beam theory equation. So we know that the deflection will be some function of m, e, I, and x, depending on what type of cantilever beam or loading situation that we have. Once we have delta m and delta n, we can then solve for the deflections in the y and z coordinate system using the inverse coordinate transformation, and then we can then take the vector sum of delta m and delta n to get our maximum deflections using this equation at the bottom of the screen here.